Yeah, so last class we discussed how concurrency can achieve at hardware level and as well the software level. So majorly at hardware level, how we can probably achieve the concurrency we have discussed by having multiple processors, and by having multiple ALUs under the supervision of a single control unit, or by having the multiple function units of an ALU, or by having the multiple functional units of a single operation of ALU, like addition for different types like integer or float or other kind. So this is all which we can rather achieve at the uh, hardware level. Okay. Now we got most of our mobiles also with quad-core processors or octa-core processors. What do you mean by octa-core? There are 8 processors running concurrently to execute different tasks at the same time to uh, you know increase the throughput of the system or your mobile, and then give the good efficiency on your programs to execute fingertips. Fine. That's how you can see now the technology has then been upgraded, getting the new devices with all such high performance speed, where you have to wait for even a while to get your required input. But then a lot of processing is going to happen behind, which you are is not aware of, rather, right? So, but then now we'll see how this concurrency can be achieved at the software level. So this can be as well achieved at the software level. It can be achieved at the operating system level. Like you got all your operating systems, multitask operating systems, time sharing operating systems, right? For example, you talk about Windows. Windows is a multitask operating system where it is allowing multiple tasks at the same time to execute concurrently, with a feeling that each of the tasks will have an assumption that it will have a dedicated processor for it. But then in reality, there's a single processor who is probably trying to listen all these different tasks which are being executed at the same time simultaneously. This kind of feeling already we are able to generate it with the help of operating systems. Uh, you know, Such operating systems are available, right? Multi-task operating system, and probably you talk about Unix operating system where you can achieve time sharing, right? Option where the multiple processors the same kind of feeling that they can think that they have their own dedicated process to keep their respective task being executed. In reality, if you see there is a single processor who is going to schedule the time across all these processes to have access to the resources based on, of course, their desired time, but then the scheduling is being synced in such a way that none of this process will be in a dilemma that somebody else is also being executed in alliance with me, rather, right? That way, kind of feeling this operating system is being brought with this, time sharing approach, where the scheduling of the processes are done in such a way that which ensures the processes will be able to have a feeling of dedicated processor, right? Okay. But then coming to programming language, if you a little going ahead of the same, coming to programming language level, right? Also, you can be able to allow the concurrency at the programming language, right? Uh, Concurrency basically can be achieved at 4 levels. One is machine instruction level. Machine instruction level, as I told you in the last class, we had a very good, discussion on how we can probably achieve the concurrency on the instructions and data, taking as two parameters, which has been classified by MJ Flins. MJ Flins is one of the scientists who have probably had given us a good taxonomy on this, concurrency, taking instruction and data as the parameters, where he has given us 4 types of classifications, given to achieve the concurrency from the hardware point of view. One is the machine, single instruction, single data stream, single instruction, multiple data stream, multiple instruction, single data stream, multiple instruction, multiple data stream. So we had a discussion of all this, how the concurrency can be achieved with all these 4 different, ways, which has been specified by MJ Flins. So this anyway majorly deals with the hardware, as we said, right? So we are more interested in knowing how the concurrency can be achieved at the programming level. So this probably has been discussed before with hardware point of view, right? Now coming to high-level language statement level, fine, and unit level. These two anyway we are going to discuss because this can be achieved through programming language, right? At the programming language level, right? And again, program level also going to be achieved through operating system here. And this is going to be done through operating system, which I just now talked about. It is multitask operating system, right? Where task is considered to be a program, of course, right? So each of the program is nothing but is a task which carries some sort of instruction to perform particular task. You can say when it comes for execution, you say it's a process, right? You say it is a process. So process and task can be intermittently used, these words, right? So multi-processing or multitask, can be achieved through operating systems, right? So many of the operating systems like Windows and all, you have achieving as this multitask operating system, of course Unix as well, right? So anyway, this program level concurrency we can achieve through operating system. Machine level, machine instruction level can be achieved through hardware, which we discussed before in my previous discussion. We can go through in detail it was discussed. And now we'll discuss these two: high-level language statement level and unit level, right? So majorly unit level can be achieved with the help of course, threads and all, right? So that has been dealt with threads in Java, and you have C++, Ada. You can probably achieve the same with the help of task. In Ada, you call it as task, of course, right? So the help of task, and in Java, with the help of threads, we can achieve this that we are going to discuss here. And statement level you can achieve with the help of some multiple processes that you have available as part of your computer. Basically in supercomputers you may find this kind of facility, or in attached array processor or array processors you can find this facility. The programming language like Fortran will have this kind of facility. When you have a single instruction to be executed on multiple data, single instruction to be carried out with multiple data. For example, you have like a vector to be carried out, a vector operation, like for example, C of 1:100 equal to A of 1:100 plus B of 1:100. It means you want to perform an addition operation on two vectors like A and B, right? With varying inputs being changed with index starting from 1 till 100, and have been after performed, the result must have to be stored, let us say, in C vector rather, right? So allowing these different of 100 operations. How many operations are 100 operations? Allowing these different operations with different processors at the same time, right? and allowing them to be executed concurrently, uh, taking only 1 unit of time on the whole, right, can be achieved with the help of programming itself in Fortran. So that kind of option is available, and which can be rather achieved through single instruction, multiple data stream as well, which I have talked about before, right? Which can be either implemented through hardware with the help of attached array processor or you know or multiple processor under the supervision of a single control unit, I will discuss, right? So that is from the hardware point of view. So provided this kind of architecture, one of these architecture is available, the programming language is allowing such kind of facility, you know, is what can be done through this kind of level, which is of course being provided by some languages like Fortran, so that we can discuss. And then here, the unit level majorly, which is going to be achieved in many of the languages that we will see through Ada or Java and others, right? So, so instruction level and program level, majorly you can achieve it at the hardware. So we are not discussing those two things, but rather the other two things we are going to discuss in detail, right? If you look at multiprocessor architectures in late 1950s, one general purpose computer and one of more special purpose processors for input and output operations are available. You may have studied computer architecture that you will find one processor dedicated for all daily operations. But in addition to the operations, there are other processor who will take care of like I/O operations and as well the communication operations. And IoT, you call it as input-output processor. Because when the communication has to happen from I/O, it's a different kind of thing because the buses are always under the control of the CPU, but then they have to be relinquished from this CPU and have to be given to the I/O so that I/O can communicate with memory directly. So this kind of approach is said about direct memory access. In order to achieve direct memory access, what is that you need is you need some kind of mechanism in between. It means when an I/O processor requesting for some data to rather read or write into the memory, then the request has to be sent to the what do you call DMA controller. The DMA controller further takes the request and then requests the CPU to release the buses. Then it releases the buses. It takes away the buses and then grant it to this IOP to IOP, so that IOP can take these buses and directly communicate with memory to read or write from the SIP. Fine. So there is some process in between that happens, right? So this all being taken care by another process, and this is going to be happened quite often in computer because when you are probably executing some program, there is always a possibility that you may need some kind of data in between through I/O. So I/O operations are quite common while being on execution. So that's the reason why, in order to take care of this kind of thing, we were having a separate processor itself, rather, right? So we call it as IOP, like Intel 8081 you talk about, or IBM 370. These are basically IOP processors, right? So you will be having one dedicated CPU, and then our general purpose processor, we call it as, and then you can have one or more IOPs also, right? Because nowadays I/O is not only coming from like just keyboard and the monitor, but then you have a lot of input and output devices nowadays available, gadgets and other kind of thing, right? So you can have multiple IOPs, and for communication purpose as well. Like basically, when the data has to be communicated across the devices, also said to be the communication, or when the data has to be out of the computer to the network, also said to be the communication, right? The communication between the system or communication between the system, right? Inter or intra communication we talk about. So for each you can have a different processor, rather, right? Data communication processor you can have, right? So it means that one general processor you find, and then one or more other processors to carry out the different operations like I/O and the communication kind of thing. Have been evolved since 1950s itself, rather, right? In early 1960s, multiple complete processes used for program level concurrency came into being, right? So program level concurrency here, multiple programs to be executed concurrently has been made possible through 1960s, rather, right? By allowing multiple complete processes parallelly being executed, rather, right? Complete process doesn't, the processor will take care of I/O and other kind of things, so in addition to ALU, right? So such kind of process have been made possible multiple in number, and then allowing the multiple programs to be executed concurrently. In mid 1960s, multiple partial processors used for instruction level concurrency. Instruction level concurrency, like when you have multiple instructions to be rather executed by different processes, rather, right? So that is being possible, and this has came into being in mid 1960s. Single instruction, multiple data stream machines also came into being. Then multiple instruction, multiple data machines also came into being after 1960s, rather, right? So these all I have discussed before, taking examples. I think that is quite clear to all of you. Now, focusing with how we can achieve the concurrency at the instruction level and the program sub-program level, rather, right? A thread of control in a program is the sequence of program units reached as control flows through the program. Basically, thread are the sub-programs, right? How we can achieve the concurrency at the sub-program level. I'm now going to talk about that. How we will achieve is the help of threads. Thread is nothing but a sub-program. It's a part of the program, right? Or you say a task in ADA, which is also similar to sub-program, right? So we'll probably now discuss in our today's session how we can achieve this thread and then program level concurrency, right? Categories of concurrency: physical concurrency and then logical concurrency. Multiple independent processors. When you have multiple independent processors allowing them to be executed concurrently, right? With a multiple thread of control, right? It means you must have a thread of control, which probably schedule. It is something like a dispatcher the other way around, a scheduler, I sometimes call it as thread of control, who will schedule these threads or multiple independent processes to have access to the resources which they are rather looking for and can execute, right? Majorly, the important resource on your computer is nothing but the processor, with the help of which only probably you want to execute your programs, right? And in addition to processors, your program may require input device, or your program may require output device, or memory. Sometimes it requires hard disk, other kind of resources as well, right? But majorly, in order to execute your program, all the time it requires is the processor. So processor, how it is going to be scheduled across the threads or the subprograms are called multiple independent processes. I say the independent programs, right? So how we are going to schedule and then allowing this subprograms to be executed concurrently is what going to be done with this particular control, right? So in physical concurrency, what happens? You will have multiple threads of control. It means each you have multiple independent processes. You have multiple processes, rather, right? And each processor can have multiple tasks at the same time to execute. It means you need to have a thread of control for each of these, rather, right? So each of the thread of control associated with this particular independent processor will take care of scheduling the tasks that are required to get executed through that respective independent processor. Logical concurrency. The appearance of physical concurrency is presented by the time sharing of one processor. Software can be designed as if there were multiple threads. So here, logical concurrency is what probably we take in our programming language to programming language level to implement, and then we could probably devise our programming such a way that we can achieve this logical concurrency in our programs to increase the throughput of our system, right? So it looks like physical concurrency, but then there is a single thread of control who is going to take care of multiple, processes to be executed through that single, dedicated ALU being executed concurrently, with a feeling that each of them can feel having its own dedicated processor at the end, right? Motivation for studying concurrency. See, as we have got lot of tasks to be carried out at fingertips rather, right? We are now, after having the technology been advanced over the time, we are becoming impatient. We don't want to wait for a while also for our requested task to be done. We want it to be done at our fingertips. We want it to happen as early as possible, which probably going towards a kind of scenario where our intuitions to be rather accepted by the computer or our gadget or device, and give us that in our required form, and almost that kind of requirement is also being fulfilled, and you can see the technology is going towards even to that level as well, right? You must have heard that the logical electronic wallpapers. Basically, when we were studying around 1907 or 8, I read somewhere in a book of Bill Gates' biography, wherein I studied talking about 3 years before, right? Almost 25 years ago. I have came to know about this. I mean, if you see that time, I'm talking about how the Bill Gates' house was built. His house was completely equipped with electronic wallpapers, right? When you enter into his house, that electronic wallpapers, which are equipped with some sensors, which can sense all your organs and your brain waves also, it can observe and then analyze the data which it receives from your brains in the form of signals, and then it will understand what you are trying to think, what you are thinking, what you want. For example, your mind is thinking of taking some cool drinks. So with the help of signals that have been generated, being accepted in these wallpaper sensors, will then analyze and generate the data, which is going to be rather passed to the respective robots who will be able to serve these cool drinks. They will immediately bring the cool drinks and put in front of your table. You feel amazed. How come this happened? When I was just thinking that I wanted to take some cool drink, but I could see the cool drinks are available on my desk. This is all been made possible some years ago itself, and we are going to get some smart cities, across the world, probably in near future. Users, a normal user, need not to be a big rich person, but could able to avail this kind of services, right? Because the technology has already been reached to that level. Okay, that level. Okay, so this was made another reason. I'm just giving you one of my example, which probably motivates for concurrency, because you want execution to be done within almost no time. And then a lot of data has to be processed at the behind. How can it all happen and then could be able to get your required thing at a very minute, not, you can't even think of a second or a microsecond, sometimes in nanoseconds, the things are being done. How this is all being happened? Because of high performance processors with all concurrent kind of approaches that are involved, involved in these, you can see. Right. So some of them which have been listed out here involves a different way of designing software that can be very useful. Many real world situations involve concurrency, multiprocessor computer capable of physical concurrency are now being used. Right? Let us say, for example, when one process has accessed the processor, at the same time other process could have come for execution with the processor. Then it will get a clash. Then automatically this will think that my processor, I thought it was a dedicated processor to me, but then it was executing someone else. It means I am not having a dedicated processor, right? So, but you don't want to get this kind of feeling among the processors on a single processor, thinking that they should have a separate, dedicated processor. How is it possible? It's possible only by scheduling them, by scheduling these processes in such a way that when one process is in execution of the processor, the other will not disturb or will not come in come in that way. But at the same time, this process will not be in a thinking that my processor is being busy with someone else, because of which I need to be waiting. I need to be in a wait mode until that is released. Fine, that also should not happen at the same time, right? But as you know that these processes, they all the time do not require only the CPU. They may require other resources as well, which are available on your system, like memory or input device or output device. So when probably the processor is busy with some other processes, at the same time the other processes also can be made busy with other resources which probably they need it, right? So that way you can probably schedule it. Even say for example, multiple processes could come for the same time to access the CPU at the same time, then you can probably put them in a queue and then schedule it as per the requirement, and then ensure that there is not much delay for each of the processes who have come for accessing that respective processor. So syncing the processes execution with the processor also need to be taken care of, right? Fine. A mechanism that controls the order in which the task should execute is what should be the synchronization, right? So there are two kinds of synchronization you probably find here. One is operation synchronization, and the one is the computation synchronization. Cooperation is like, for example, when you have a task A, must wait for task B to complete some specific activity before task A can continue its execution. For example, producer-consumer problem today, right? Where producer is going to produce some item. Producer is going to produce some item into the buffer. There is a buffer you have. Then the consumer can consume it, right? Fine. So there should be some kind of synchronization among these two different. These are two different processes, right? But when producer produces some item, only then the consumer can consume the same from the buffer. That means there must be some kind of cooperation. That cooperation should be in both the ways. Of course, the consumer must have to wait until the producer produces the item into the buffer. It means it must wait until producer produces. At the same time, if let us say the buffer consists of only place to store one item at a time, then until the item is being consumed by the consumer, producer must have to wait to produce the item into the buffer. So some kind of mutual, cooperation needed among these two processes while accessing the shared resource. Like buffer is the resource being shared by both the producer and the consumer. Fine. Similarly, computation synchronization. Computation synchronization is something like two or more tasks must use some resource that cannot be simultaneously used. For example, shared counter. You have a counter, fine. Let us say whose value is some 10 or something like that, right? There are two different processors, A or B, let us say, or multiple processes. It means more than B also, more than two as well, right? C, D as well, no issue. So here, let us say this counter, which is being shared across these different processes, when probably trying to access it, when they read it, they can read it, at the same time, no issue. They can take the value, right? But then when they are writing into it, only one at a time can do it, right? If writing is allowed, by each of this processor at the same time, then consistency will not be restored. What do you mean by consistency? The data which has to be updated, as what it has to be updated at all the places rather, right? Fine. So that cannot be restored rather, right? So while writing, you can allow only one process at a time. Reading can allow multiple processes to rather access it at the same time. But writing operation, when it comes here, you can allow only one process at the same time. It means you will be preventing the other processes from being accessed while one is writing. This kind of synchronization is to be the computation synchronization. Fine. So these are the two different types of synchronization. Generally fine. Let us look at this example how the computation synchronization is going to be achieved. What kind of issues you may probably find with. Let us take one variable total. Total value is, let us say, 3. And here there are two tasks, A and B. Would like to do some operation on this total. Okay. So generally, when an instruction has to be executed, as I have discussed in the last class, what are the different phases that you have to go through in order to execute an instruction? What is that first? We will first the instruction, fetching instruction. Fetching is instruction is nothing but accessing that instruction from the memory, rather, right? Accessing memory will take considerable amount of time, so we'll consider as a separate phase. Okay. Fetching instruction, then you decode, then you calculate the effective address, probably if the operand is specified with different kind of addressing mode. Then you are going to execute the, fetch the operand. Then you are going to fetch the operand after you calculate the effective address as well. Then you execute the operation, then you store the result, right? Let us take only 3 out of this: fetching, operation, and store. I'm considering only 3 of these phases. Basically, these are the different phases that we find in instruction execution. But then, majorly, let us look at 3 into consideration: fetching, execution, and store. Okay. Consider the operand is not specified with any addressing mode, then you don't require this. And thinking that decode and execute will take, decoding is taking less amount of time, so which can be rather combined with execute. And storing, since it has to access the memory, so it is taking considerable amount of time, for which I have a separate phase. So let us taking 3 phases: fetch, execute, and store. Okay. Let us take these 3 phases. Now, what happens when you are trying to perform some operation on total? So, these 2 processes, task A means A process A and process B, both would like to perform certain operation on total. Okay, total, whose value is 3 initially. And in order to execute, any instruction, it has to go through these three phases: fetch, execute, and store. Okay. Let us now take task A. Task A would like to perform some addition operation. It wants to add to total value. Okay, add 1 to total value, existing total value. And task B, what task B wanted to do, it wants to multiply the existing total value by 2, let us say. These are the two different operations, but required to be rather performed by two different processes, A and B here. Okay. Now, let us say this total is a shared resource which can be accessible by any of the processes at the same time. So, let us say A has accessed or fetched. Since every of the instruction has to go through three phases, so three of them are going to be done in separate clock pulse, fine, independently, and both can be allowed concurrently. So it means task A and task B both can be executed concurrently, their respective executions, their respective instructions. So now what happens, look at here, when task A first fetch the total, fine, because first the fetch instruction has to happen, then execute, then store. So when it fetches the total value, what does it get? It will get 3 here. Yes, sir. It will get 3 here as total value. So total will be 3 here. Yes, sir. And then what it happens until it goes for add operation before task A go for add operation. Even task B also can start its execution, right? So it has now fetched the total value. When it also has fetched the total value, that also to be found as 3 itself here, right? Yes, sir. Why? Because the time when task A and task B both are trying to access the total value was 3 only, right? Total is 3. So here when it has fetched, it has got 3. Maybe task B has started or initiated its instruction execution while after the task A started. But then before the operation of task A, so a total must be here at both the places. You find 3 itself. Okay. Now what happens when task A enters into the execute phase, where the execution of its instruction has to happen, should add 1 to the total. So when it add 1 to the total, what will be the total value now? Total value here now becomes what? 4. Okay. It becomes 4 here. That's good. But then it is associated with the task A itself. It is not restored, rather, right? It is not restored so far. Now what happens? Task B enters into the execute cycle. When it executes into the execute cycle, it can find total 3, and when it is multiplied by 2, then total becomes what? Total becomes here 6, right? Here total becomes 6. Now, when it is going to store means restoring the value into the total from where it has fetched. So now task A wants to store the total value. So when it goes to store the total value, that was 3 before. Now when task A stores with the change total value, that total value becomes what? Now 4 here, right? It becomes 4 here. But then after a while, task B comes and then it also stores the total value. Then what happens? The total value will be restored with 6. So what is happening at the end? You can find the total value as 6. Okay. So you can see if I have to perform addition and multiplication both on this total, what must be my value? 3 plus 1, 4, 4 into 2, 8 I should get. But I did not get 8. Since the operations were not sequenced, they are concurrent, because you are allowing the operations to be executed concurrently, fine. But then when they are executed concurrently, what is happening? The expected output, I am not getting it as what I am basically looking for. Fine. Yes or no? Why is it happened? Because you can see the instruction also when being executed in 3 different phases, and both these instructions are accessing that shared resource at the same time. When it fetches, once it fetches, then it goes for the execute. So, and both of them are concurrently executing the value that they have fetched. But at the time of restoring the value, you can see that restoration is done one after the other. So, and the result is happened in the different way. Let us say the store could have happened task A, store of task A done before task B. This is what the result is. If store of task B happened before task A, then what will be the result? The result will be different. You may find the value as 4. You may find the result as so. Neither of the result is correct. Even if the task A store operation is done before, or task B store operation is done before, in both of these cases, the result which you may get either 4 or 6, but both of them are not correct. Why? In order to have my expected output, if the operations are happened, if both the operations are happened one after the other on this total value 3, I must have to get what? 8. If A is first, then B is second. If B is first and A is second, then I must be getting some other result. What is the result? I'll be getting 6 plus 1 is going to be 7. So even in that situation, so how I am allowing this task to get executed, in what sequence I am allowing this to get executed is also going to matter here when you are going to allow the shared resources accessible by multiple processes at the same time and do certain modification on the particular respective resources. Fine. So the result which you may get is not as you expected, right? So this is one of the issue, of course, rather has to be addressed while you are basically allowing computation synchronization. So how you can allow is with the help of certain solutions, like we have semaphores and monitors that we are going to study in the coming slides. Okay, when you look at the process, when a process is in execution, you find different phases. Fine. So these are the different phases across which every process must have to go through until it finishes execution. New, when it just starts, it will be in a new state rather, right? And then runnable or ready state. Then it goes for execution. This will be the running state. Then due to some reason, because of its own reason, like it wants to read some data from the IO, or waiting for some event to occur, or some other high priority process could have preempted the resource from it. Because of various reasons, what happens, the process which is running get blocked, right? So that is said to be the blocking state. And the blocking stage, processes may resume back again. When they resume back, they have to again come to the runnable or ready state. Again, they can go for execution like this. Okay. But then once the execution of the program is done, it will be terminated. You say it is an exit state or stop state, right? Exit or terminate or stop state, right? Sometimes what happens, the process who was running get blocked for some reason, is blocked for is blocked relentlessly for a longer enough time, okay, losing its liveness. Then such state is said to be the dead state, right? So the processes who are dead, they cannot be revoked back. Fine. So this is how you can find different phases in which a process may lie in once it get initiated, right? All the processes will start with a new state. When probably you invoke the process rather, right? You say it is a new state, or you are allowing the process to start its execution. But then there must be already certain processes who are in queue to access the resources and to start its execution. So all such processes, they are available in a queue, ready queue, right? You must be studying data structure, then you will find a queue data structure. So queue data structure is being used here to store all the processes who are waiting for a processor or the resources to access and then go for execution, right? So all such processes you can find in the ready queue once they are started. Okay, then based on the schedule, I mean there is a scheduler here who will be controlling and who will be deciding which particular process have to be given the resources so that they can start their execution. When they are given the resource only, they can go for execution, right? So when it was given and it is allowed to go for its execution, and it is when executing, we say it is the running state, rather, right? So here the scheduler is going to schedule all such processes, the sequence in which these processes have to go for its execution, right? You have different kind of scheduled mechanism. You study as part of operating system. First in, first out, shortest job first, priority scheduling, the different kind of scheduling algorithms you generally find. Okay, so the schedulers who are going to schedule the processes, the sequence in which they can go for execution. So once they are allowed to go for execution, they are in running state. Once they are running, due to some reasons, as I said, while executing, you have some scanf statement. For example, if you are executing a C program, you have a scanf statement. Scanf requires some data from the input device. Then what happens? The execution will be suspended for a while from the CPU, and then it has to go to IO device, right? So IOP comes into picture, and then with the help of direct memory access, the IOP will conduct the IO transfer for your process. Fine. This is all going to happen by being blocked for a while, right? So when such kind of situation is coming, it is by self, rather, right? By self, when it is happening, also it is being blocked. Or sometimes what happens, this process is going to be suspended by some other process. Let us say the processes who are there in the ready queue. If you are scheduler is implementing the preemptive scheduling, then what happens? Higher priority process when comes into the ready queue, they will straight away go and then snatch away, relinquishes the CPU from the running process. Fine. Then what happens? The running process has to be suspended. They have to be again in a blocking state until that particular resource is going to be released by that respective process who have relinquished the CPU from you, right? So this is all going to happen because of various reasons, I said, right? Or sometimes the program itself is waiting for some IO event to occur, or some subsequent event to occur. There is a self suspension, or could be suspension by someone else. Because of both of these reasons, the processes get blocked for a while. But then, after being blocked for a certain while, they may again resume, right? When they resume, they have to again go to the runnable state, ready queue. Again, the scheduler will schedule you to go for its execution, go for your execution. You can probably allowed to have access to that respective resource, and then you will then execute. Fine. If your execution is done, completed, then you will terminate from the system. We say it is a stop or exit process, rather, right? Otherwise, let us say if it is again get blocked due to some reason, it will be blocked here and resume. When it resumes again, it has to come to the runnable or ready queue state. From there, after scheduler schedules, then you can come to running, and then you can. So it's a kind of cycle. But then what happens? Due to some reasons, the processes which are under block mode will be blocked for a longer enough time. Okay, it happens because of certain reasons, like all the time. Let us say the processes who are coming are entering into the ready queue or with the higher priority, and you have allowed the preemptive scheduling. So all the time they may relinquishes the process on the lower priority processes, and they are trying to execute their own. Then what happens? These lower priority processes every time they need to get blocked even after they've been scheduled as per their slot. Fine. So because of being waited for a longer enough time, they may lose its liveness. When they lose their liveness, they cannot be further resumed back. So such kind of processes are said to be the dead states. They will be, they will be rather, terminated from the system itself. This is one reason why the process get dead. But then there are other reasons as well, because of which the dead state may happen. There are 4 different situations. Probably you may find mutual exclusion, hold and wait, circular wait, and preemption, right? These are certain reasons because of which, of course, what happens, the processes get blocked for longer enough time, losing their liveness and entering into the dead state. Then that process cannot be resumed back again. These all things you will to study in operating system in very much detail, but then probably I'll give you a brief about the same in the next class. Okay.